Welcome to General Chemistry. I'm Jim Burnham. Today we're going to talk about scientific measurement. This is Chapter 3. Chapter 2, we talked about the various states of matter, solids, liquids, and gases. And now we're going to talk about how important it is to make correct scientific measurements, how to do it, what to do, what not to do. Making correct measurements is fundamental to the scientific effort. In chemistry, we are going to use the International System of Measurements, known as the SI system from the French. Not all measurements give the same information. Say someone has a fever. You could put your hand on her head and say, yeah, she feels warm, she feels feverish. This would be an example of a qualitative measurement. This is a measurement that doesn't involve any numbers, but it simply says, oh yeah, her forehead feels hot when it normally feels, normal. So qualitative measurements give descriptive, non-numerical results. Hot, cold, tall. Or you could use a thermometer and you could get a numeric value, and that will give you a quantitative measurement. Quantitative measurements give the results in a definite form, usually as numbers and with units. So you might say, oh yeah, she has a temperature of 101 degrees Fahrenheit. But even definite measurements, like those taken with a thermometer, are only as reliable as the instrument used and only as reliable as the technique used. So, as we're going to see shortly, every measurement has a certain measure of uncertainty. And we try to express that with a concept we'll talk about a little later called significant figures. So here are some common measuring things. This is a thermometer to measure temperature. Here is a radar gun to measure speed. Here is a grocery scale to measure weight. So lots of ways that we can take measurements, lots of different instruments. We need to talk about scientific notation. In chemistry, we will encounter numbers that are both very, very small and very, very large. For example, the mass of an atom of gold is 0.00000000327 grams. That is a very, very small number. 1 gram of hydrogen contains 602, I happen to know this is hextillion atoms. That's an astonishingly large number. So to work more easily with such large and small numbers, we use what is known as scientific notation. Scientific notation is the product of two numbers, a coefficient and a 10 raised to a certain power. So this is what it will look like. Let's say I want to express the number 45,000 in scientific notation. I'm going to reduce this number to a number between 1 and 10. So it's going to be greater than 1 but less than 10. And it turns out I can do it as 4.5. And to do that, I'm going to have to come over 1, 2, 3, 4 decimal places, or 4 tens. I'm going to come over 4 tens. So I'm going to express this number as 4.5 times 10 to the 1, 2, 3, 4. So 4.5 times 10 to the 4th. Small numbers, they'll simply have negative to 10's raised to negative powers. So 7.6 times 10 to the negative 4, I would express this as 0.00076. So the coefficient, as I mentioned, is always a number between 1, so it's 1 or more, but less than 10. The exponent tells us the number of times the coefficient is multiplied by 10, or if the exponent is negative, by 1/10. So numbers multiplied by 10 are going to get increasingly large, and numbers multiplied by 1/10 are going to become increasingly small. For numbers greater than 10, the exponent is positive and equals the number of places the decimal point has been moved to the left. For numbers less than 10, the exponent is negative and equals the number of places the decimal has been moved to the right. So again, 52,314, we move it 4 places, 1, 2, 3, 4 to the left, and we express that as 10 to the 4. So this number is 5.2314 times 10 to the 4th. How about 3.2? How would we express this? Well, there's no need to move it. It's already a number between 1 and less than 10. So we leave it the same, and we just leave it 3.2 times 10 to the 0. 10 to the 0 is any number to the 0th power is just 1. So 3.2 times 1 is 3.2. How about this small number? Well, we're going to move this number 1, 2, 3, 4, 5 places to the right to get 4.28. 4.28 times 10 to the negative 5. Again, we're going to move 1, 2, 3, 4, 5, 6, 7, 8 places to get 6.02 times 10 to the 8th. How about the atoms in 1 gram of hydrogen? As I mentioned earlier, this is 602 hextillion. So we would move this over 3, 6, 9, 12, 15, 18, 21, 22, 23. This would be 6.02 times 10 to the 23. And I want you to remember this number because we're going to encounter it in future chapters. This is a funny number. It's known as Avogadro's number. It's the number of a mole. Just keep that in the back of your head. We will see this number again many, many times. Multiplying with scientific notation. So when you have scientific notation, you're multiplying two numbers expressed in scientific notation. You're going to multiply the coefficients, and then you're going to add the exponents. For example, 3.0 times 10 to the 4th times 2.0 times 10 to the 2nd. You're going to multiply the coefficients together, 3 times 2, and then you're going to add the exponents of the tens together. So this is going to be 6 times 10 to the 4 plus 2, 10 to the 6th. How about dividing with scientific notation? Again, you're going to divide the coefficients, and instead of adding the exponents as you did in multiplication, you're going to subtract the exponents. So here's the same number. We're going to divide this time. 3.0 times 10 to the negative 4 divided by 2.0. So you're going to divide the coefficients, and you're going to subtract the exponents. And you're going to get 1.5 times 10 to the 2, 10 to the 4 minus 2. Addition and subtraction with scientific notation. So this you have to make a change, and this is something that it's different from multiplying and dividing. Multiplying and dividing is relatively straightforward. With adding and subtracting with scientific notation, before you can add or subtract the numbers written in scientific notation, you must make the exponents the same. So you're going to have to make the tens with the same exponents. Why? Well, because the exponents determine the location of the decimal points. And those decimal points have to be aligned before you can add the two numbers together. So for example, when adding 5.4 plus 10 to the 3 to 6.0 times 10 to the 2, we have to adjust the exponents to make them the same. So we can choose to adjust the 6 to a 10.3 by just moving this over one more. So it would be 0.6 times 10 to the 3. And now it has the same base, it has the same exponent as this. And so we would add 5.4 plus 0.60, both bases by 10 to the 3. So we'll add this, and they'll both be times 10 to the 3. So that's what it looks like. Now this takes us to a very important topic known as uncertainty. Every measurement has a certain degree of uncertainty, and we have to express that uncertainty. I'm always saying a measurement has to express two things. It has to express the amount of uncertainty in the measurement, and it has to express the units of the measurement. A number without a unit, a number without expressing the level of uncertainty in the measurement is not a useful number at all. Now this takes us to the issues of accuracy, precision, and error. Ideally, you want your measurements to be both correct, that is, accurate to the known standards, and you want them to be reproducible or precise. Every time you take the measurement with whatever instrument you're using, you should get very, very close to the same number. Again, within a certain degree of uncertainty, but it should be very, very close. That shows the precision of the instrument and perhaps the technique used. So accuracy is how close a measurement is to the actual or true or standard value. So a good example of this would be hitting the bullseye. That's where you want to hit, and if your measurements hit that, then that's an accurate shot. That's an accurate measurement. Precision, on the other hand, is how close a series of measurements are to each other. And measurements can be very, very precise, but also inaccurate. They could be precisely wrong. So you could have a systematic error in your measurement or a systematic error in your technique, and cause you to get a very, very wrong number. It's not accurate at all, but it's very reproducible. You're getting the same error over and over again. So again, ideally, you want to be both accurate and precise, but precision is how close all the measurements are to one another. So it involves multiple measurements and how closely they track to each other. So going back to our example of a target, this would be an example of something that is neither accurate nor precise. We're not hitting the bullseye, and our measurements are not very close to one another. Here's a series of measurements or shots, arrow shots or bullet shots or whatever, where they're very, very close to each other. So we would say this is a very, very precise grouping of measurements or arrows, but it's not very accurate. Everything's shifted over to the left. All those should really be right here in the bullseye. Here's something that's accurate, but not very precise. They're all in the bullseye, but they're not very close to each other. At least not relative to something like this or here. This would be the ideal, where your measurements or your arrow shots are both accurate, they're in the bullseye, and precise, they're all very tightly grouped together. What is percentage error? Well, percentage error, so error, just any error, is the experimental value minus the accepted value. Because unless you're performing a new experiment that's never been done before, someone else has performed that experiment multiple times, and it has been done accurately and over again, and to the point that it has gained an accepted value, a reference value. So the error is what you might get if you did the experiment, and then you would check that against the accepted value, and the error would be the difference between those two numbers. Percent error is going to be error, which we take here, experimental value minus accepted value. We're going to take the absolute value of that, because as you can readily imagine, your experimental value might be bigger or smaller than the accepted value, and so when you subtract the accepted value, you could get a negative number. So we just take the absolute value of that difference, whatever it is. So we take the absolute value of the difference between your measurement and the accepted value. We divide it by the accepted value, and we multiply it by 100%. That gives us percentage error. That's the formula for calculating percentage error. Significant figures in measurement. This takes us to the always entertaining issue of significant figures. As I said before, every measurement contains some level of uncertainty, some estimation in the final digit. And that's why we don't include unlimited digits in our measurements. We include the number of digits that we're certain of and one additional estimated unit. And that last digit, that estimated digit, that is where the uncertainty is. All the other numbers are certain, but the last number is uncertain. It's not one you're going to fight about. Someone else could do the same measurement, and their number might be one higher or one lower in that final digit because of the estimation involved. So let's look, for example, at a practical application of this that shows uncertainty in measurement. If I asked you to give me the value of the water, let's say, in this beaker, you might say, well, it's more than 10, it's more than 20, it's less than 30, it's somewhere here between 20 and 30. I might call that 27. Someone else might call that 28. But that's as far as we can go. We would stop after that, because that last digit, that 7 or that 8, that's an estimation. We wouldn't just go, oh, that's 2.83516962. What? Where did you get that? You have no justification for any of those numbers beyond the 7 or the 8. Now, if we have something with more gradations, then we can make our measurement more precise. So we can look at this and go, okay, well, this is now it's more than 28, but less than 29. So let's estimate. It's 28 and maybe let's say 3/10. Or someone else might say 2/10 or 4/10. But whatever it is, that's as far as we can go. If we wrote this number out, we'd say 28.3, 0.2, 0.4. That last number, the 0.2, 3, or 4, would be our uncertainty. Let's say we had something that was even had more gradations and more precision. Now we see that it's 28.1, 2, 3. Oh, it's 28.3. And what's this last one? A little bit over, maybe 1. So we might write this number as 28.123. We're certain about that. And then our last estimated number is 1. 28.31. And we stop. We don't keep adding numbers because we don't know any precision beyond that 0.1 or the 0.31. So in any measurement, we put down all the numbers we're sure of and one that we're unsure of, the estimated. And that number of digits, including the one uncertain digit, is called the number of significant figures, which we abbreviate by succinct sig-figs. Calculated numbers depend on the number of sig-figs used. So often we will make a measurement, we'll express that measurement in significant figures, and then we'll do a calculation involving those numbers. And our answer is not everything that the calculator might show on the screen. The answer that we can use depends on the number of significant figures used. And there are some very precise rules that we're going to go into about how to use significant figures. So here they go, the rules for sig-figs. Rule 1, all non-zero numbers are significant. So if it's not a 0, it counts. This number has 3 significant digits because all of them are non-zero. Rule 2, captured zeros. Zeros between 2 non-zero digits are also significant. So this 0 is between 2 other non-zeros, so this is a captured 0. This 20451 has 4 significant figures. So far so good. Non-zeros are significant. Good, got it. Captured zeros are significant. Got it. Leading zeros are not significant. They are nothing more than placeholders. The number 0.54 only has 2 significant figures. This 0 is just holding the place. It's just saying, hey, here's where the number begins. It's 0.54. How about this one? This 0 and this 0 and this 0 also are just holding the place. And it's telling us here, now we have 2 significant figures. So leading zeros are not significant. You ignore them when they're there. You ignore leading zeros and you only count the numbers after the leading zeros. Rule 4, trailing zeros. Trailing zeros in a whole number without a decimal being shown are not significant. So if we write the number 540, this indicates that the 0 is not significant because it's just a trailing 0 and there's nothing behind it to say, hey, this is really there. We could write this as 540 with a decimal point to indicate that all 3 of those numbers, 5, the 4, and the 0, are significant. But without a decimal point, we ignore this trailing 0 and we only count the first 2 numbers as significant. Rule 5, if it does have a decimal point, then you count it. Trailing zeros with a decimal shown are significant. So 540 with a decimal point, we would consider that to be 3 significant figures. Mostly you don't see this very often. What you will see if someone wants to express this as 3 significant digits, they'll use scientific notation. And that's one of the great advantages of scientific notation, is it is very, very clear about which zeros are significant and which ones are not. So you may never encounter this, but if you do see a number with a decimal, it means count everything. That decimal means that is not a throwaway 0, it's important. How about trailing zeros after a decimal point? Yes, trailing zeros to the right of a decimal are significant. So there are 4 significant figures in 92.00. 92.00 is very different from 92. This 4-digit sig-fig number is different from this 2-digit sig-fig number. A scientist who measures 92.00 millimeters knows his value to the nearest 100th of a millimeter. That's what this is. This is to the nearest tenths. This is to the nearest hundredths. And this guy has done the work down to the nearest 100th. His level of uncertainty is in this hundredths of millimeters. Whereas his colleague who only measured 92 millimeters only knows his value to the nearest 1 millimeter. So this guy, his number is 100 times more precise than the measurement by this guy. So it's important to know that 0 doesn't mean nothing. 0 denotes actual information, just like any other number. But you can't just add on zeros that aren't certain to belong there. You can't, if you only measure something to 92, you can't just put a decimal and start stringing zeros behind there, because that implies that you actually have done the measurement down to the tenth and the hundreds and the thousands and the 10,000th and so many, however many zeros you wrote down. Finally, rule 7, exact numbers. Exact numbers have an unlimited number of significant figures. So this applies to numbers that are defined quantities. For example, we define 1 meter as 1 meter is the same as 1.00 meters or 1.0000 meters, whatever. 1 meter is a defined quantity. So we don't just say, oh, I multiplied by 1 meter. If it's a true meter that you're talking about, it has an unlimited number of significant figures because it has been defined. This also applies to exact counts. For example, if there are exactly 23 students in the room, then this whole number 23 has an unlimited number of sig-figs. So defined counts and exact counts have unlimited sig-figs. So let's look at how to use sig-figs in calculations. The rule is this: the answers cannot be more precise than the measured values used. Your answer can't have more significant digits in the answer than you used to create those answers. It is a great concept that a chain is only as strong as its weakest link, which means one weak part will render the whole part. In our case, one weak measurement wrecks all the precision of the other measurements. If you measure one measurement to a whole number, and then you measure all the other measurements to the nearest 100th of a decimal, you can't use those hundredths because your answer is only as strong as your weakest uncertainty, and your uncertainty is in single digits. So you're not allowed to use anything more precise than that. We'll see. So the answer can only be as precise as the least precise value used. In addition and subtraction, and note, the rules for adding and subtracting sig-figs are different from the rules for multiplying and dividing. In adding and subtracting, the least precise value is the one with the fewest digits to the right of the decimal. Okay, so if I've got one answer that goes to the nearest single digit, let's say 21, and I add it to a number that is 32.3, the 21 has the fewest digits to the right of the decimal, has none. Whereas the 33.2 or whatever, that has one digit decimal to the right. So I'm limited by whichever number has the fewest digits to the right of the decimal. So let's see how this would look. Let's say I'm adding 12.52 meters, which has 2 digits past the decimal, and I'm adding 349.0 meters, which only has 1 digit past the decimal. Oh, and this is significant because it is after, it's after the decimal point. And let's add 8.24, again, 2 digits past the decimal. What is my limiting, which is my least precise measurement? Well, this one that only has 1 digit past the decimal. That means in my answer, I can only keep 1 digit past the decimal. So I do my addition, and I note that my calculator is going to give me 2 digits past, but I know I can only keep 1. So I look at this final number here that I can't keep. If it's a 5 or more, I round it up. If it's 4 or less, I round down. In this case, I round up. So I would say 369.8 meters. I can only keep one digit past the decimal because that I had 1. Now, if all 3 had 2, then I could keep 2. Let's see how this works in subtraction. Same way. This number has 3 digits past the decimal point. This number only has 2 digits past the decimal point. I'll do the math, but I can only keep 2 digits. So 46.286. I look at this number that I can't keep. Is it 6 or is it 5 or more? I round up. 4 or less, I round down. I round up. 46.29 is my answer. Okay, how about multiplying and dividing? Again, the answer can only have as many sig-figs as the least precise measurement. So in this one, we just count sig-figs. Here, we count numbers past the decimal. Here, we count the number of sig-figs in the multiplying and dividing. All right, so that's the difference, and you have to keep that in mind. Some people just like to only count the number of sig-figs, and that works perfectly for multiplying and dividing, but when you go to addition and subtraction, it's not the same. These all have 4 sig-figs. This has 3 sig-figs, but this doesn't limit us. What limits us is this, the number past the decimal. Okay, multiplying and dividing. So this number has 3 sig-figs, and I'm multiplying by a number that has only 2 sig-figs. Again, this is a leading 0. This number only has 2 sig-figs. So even though my calculator will show me 4 significant digits, I can only round to what? To 2 sig-figs, because that's the least amount of sig-figs in my least precise measurement. So even though I have a bunch of numbers to work with, I can only keep 2, which means I'll look at this third number and ask myself, do I round up or down? I round up because it's 5 or more. And so my answer is 2.6, and that's it. I stop. I don't write any more numbers because I'm not allowed. I have no confidence in those numbers because this is I only had 2 sig-figs. So my confidence runs out after 2 sig-figs when I'm multiplying and dividing. Dividing, same thing. Here I have a number with 1, 2, 3, 4, 5 sig-figs, but I'm dividing by a number with only 2 sig-figs. So how many can I keep? I can't keep all 5 or even more. I can only keep 2. So again, what do? Do I round up or down? I look at this third number. It's 4 or less, so I round it down, and I just keep these last 2 numbers, 0.29. And I'm limited because I divided by a number with only 2 sig-figs, so my answer can only have 2 sig-figs. Please note that the position of the decimal point is only relevant to the rounding of addition and subtraction problems. So we don't care about the position of the decimal point when we're multiplying and dividing. We only care here about the number of sig-figs in every calculation. And our answer is limited to the least amount of sig-figs that we used in the calculation. So here's some practice things you can do. How many sig-figs in each of the following? Okay, 1, 2, 3, 4. Okay, these are captured zeros, so we count those. This is a trailing 0, but it's after a decimal point, so all 5. Okay, same thing. This 0 is after a decimal, so we count it. 4 sig-figs. How about this? We have 2 captured zeros and a trailing 0 with no decimal point. So we get rid of that guy, and we just keep these 2 zeros, and so we have 1, 2, 3, 4, 5 sig-figs. Okay, here we have scientific notation. Scientific notation is always, everything written in scientific notation is significant. So all 3 of these numbers. Here, these are just leading zeros. We can ignore them. They're just placeholders. We have 2 sig-figs. Here, these are all trailing zeros with no decimal, so we ignore all of those numbers. This only has 2 significant figures, even though it's a very big number. Okay, some others here I can let you look at. Just if you want to, you can pause the video and do these calculations and check your answers. This will give you some good practice using sig-figs. Your calculator will give you a lot more numbers oftentimes than you can use. So don't be thrown off by that. You can only use what, in this case, what is limited by your least accurate or your least precise calculation. Here's another set of practices you can use for addition and subtraction. And I encourage you to go through these because these will really help hone your sig-fig skills. Now let's turn to the International System of Units, the dreaded metric system. Every measurement, as I said, must be expressed in 2 ways. In the correct number of sig-figs, which tells me where my uncertainty is. That last number is my uncertain number. And in the correct units. A number without sig-figs or units is not a measurement. It is nonsense. So a number without a unit is worthless. A number without a number that doesn't express the correct number of sig-figs is likewise worthless. If someone says walk 6 in this direction, your response would be 6 what? 6 feet, 6 meters, 6 yards, 6 miles? Walk 6, that 6 is useless without a unit. So the standard of measurements used in science universally is the metric system. And I know here in the States we don't like to use the metric system much, but hey, this is science and we got to get on board. This is what's at. This is the news. This is the new cruelty. You can continue to use the other measurements in your day-to-day life, but when it comes to science, when it comes to chemistry, we're going to use the metric system. So, what is the metric system? Well, it's the SI system. What are the advantages? One huge advantage of the SI system is it's based on the decimal system, which means everything is in multiples of 10. And that is very, very convenient and useful. And it obviously lends itself very easily to being expressed in scientific notation because, again, that's based on powers of 10 as well. Units can be expressed in terms of small or large units by changing the prefix. We'll see this. And the prefixes are the same for all units. So the metric system, for all its annoyances to us Americans, is actually a very well thought out system. And once you get the hang of it, once you know what the prefixes mean, they always mean the same. So that's what we're going to use. We're going to change the prefixes to change the number of whatever unit we're talking about. So here are the 7 base units of the SI system. For length, the unit is the meter. Here's its abbreviation. For mass, the kilogram. For time, seconds. For amount, mole. And we're going to hear a lot more about the mole in chapter 6. For temperature, it's Kelvin. Kelvin. Not Celsius as you might expect, and certainly not Fahrenheit, but we'll get to that later. Electric current, it's ampere, and luminous intensity, it's candela. So those are the 7 base units for the metric system. Now, some of these units can be derived from these base units. So, for example, the base unit of length is the meter. Volume is simply length times length times length. It's width times length times height. And so we can get to the volume, which is simply 3 of these meter units. Kilogram, density. Density is mass divided by volume. So you're going to see some of the ones with asterisks, those are the base units. And the ones that don't have the base units, those are either non-SI units, like the liter, which we still use in chemistry. Particularly, we use the millimeter, so 1,000th of a liter, milliliter. Degrees Celsius we also use, even though it's a non-SI unit, because that is just more common. Atmosphere we use, millimeters of mercury, calorie, and so on. So there's several non-SI units that we still use in science, even though they're not, strictly speaking, part of the metric system. So here is a great summary of the units of the metric system. So here are the base units we went through. Here are the derived units. So they are based on multiples of these units. So hertz, for example, is 1 over seconds. Well, that's 1 over this. So here's the base unit. Here's the derived unit. Force is meters times kilograms times or divided by seconds squared. And so this name, the Newton, this quantity or whatever, this derived quantity is made up of these base units. So you can derive a lot of other stuff using these base units. But here's the thing I want to focus on now. This is, if you learn these, you will have all of the knowledge that you need to navigate the metric system. Let's start from here. So deci means 1/10. So if we just started with meter, meter would be 1. Okay, a decimeter would be 1/10 of a meter. A centimeter would be 1/100th of a meter. A milli, 1,000th of a meter. Micro, 1 millionth. Nano, 1 billionth. Pico, or pico, I don't know. I think it's pico, is 1 trillionth. Now that's getting smaller and smaller. We can also get larger and larger. So again, if we had a meter is 1, a decameter would be 10 to the 1 meters, or 10. Hecto would be 100. Kilo, we don't use hecto and deca much, but we definitely use kilometer. That means 1,000 meters. Megameter means 1,000,000. Giga means 1 billion. And tera means 1 trillion. So here are the numerical values. We can go from 1 trillion down to 1 trillionth. And so if you know these prefixes, they're the same whether we're talking about meters or kilograms or seconds or anything else. So memorize these prefixes. If you do it now, it will save you a lot of time and frustration in the future. Also memorize these symbols. So micro is this weird looking M. Milli is a regular M. Centi is a C. Kilo is a K. Mega is a capital M, and so on. Here is a mnemonic to help you remember this. The great mighty King Hector died unexpectedly drinking chocolate milk Monday night at the Monday night pictures. The great mighty King Hector died unexpectedly drinking chocolate milk at the Monday night pictures. That is a mnemonic to help you get tera, giga, mega, kilo, hecto, deca, the unit, whatever it is, meter or whatever, any of these other base units, kilogram, deci, centi, milli, micro, nano, and pico. So I don't know if this will help, but if you want to go from trillion to trillionth, the great mighty King Hector died unexpectedly drinking chocolate milk at the Sunday night pictures. This is just another way of expressing this. Yet another way. Oh, this is just measures of length. So when we talk about length, the measures we typically use are the meter and the kilometer. Those are the two we typically use. And we can convert these because we know milli means 1,000. 1 meter is going to be 1,000 millimeters. And 1 meter is going to be 100 centimeters. And again, just like we talked about before, since these are defined quantities, these have unlimited numbers of significant digits. So if you use either of these as a defined unit, you wouldn't say, oh, this only has 1 sig-fig because these are trailing zeros. No, this has, as a defined unit, infinite sig-figs. When we talk about weight, the units we're going to use are the gram. And in chemistry, we use the gram a lot more than the kilogram. Kilogram is 2.2 pounds. That's a lot of material to use in an experiment. So we typically will use things in the gram range, which is 1,000th of a kilogram. And 1,000th of a gram is a milligram. So you'll see grams and milligrams much more than you'll see kilograms. And when it comes to measurements, we use the liter, but more frequently we use the milliliter, the 1,000th of a liter. So these are the ones you're going to see in chemistry. Units of volume. Now this will help you visualize the relationships. 1 liter equals 1,000 milliliters, as we saw that before. Oops, we saw that right here. A liter equals 1,000 milliliters, and that makes sense. Milli means 1,000th, so it takes 1,000 of them to equal the unit. So this volume here is a liter. It's also 1,000 milliliters, and it's also 1,000 1,000 centimeters. It's 1,000 cubic centimeters. And this is a relationship I really want to point out to you. You will need this a lot. But volume, these are equivalencies. 1 cubic centimeter is the same as 1 milliliter. And this is important if you ever have to convert from length, because this is a unit of length, and this is a unit of volume. And because they're equivalencies, you can use these to convert from length to volume. In any case, this will help you really, you'll see this. So as you can see, this is 1,000 centimeters because you have a 10 times 10 cubic centimeters, that's 100, and then you have 10 rows of 10, so that's 1,000 cubic centimeters, which is equal to 1,000 milliliters, which is equal to a liter. Another way of expressing that, but here is the key relationship that you have to lock this away. Don't forget. So 1,000 cubic centimeters equals 1,000 milliliters, because one equals one here. And therefore 1,000 cubic centimeters equals a liter, just as 1,000 milliliters equals a liter. Have I said it enough? You've got to remember that equivalency. Okay, how about units of mass? We often use weight and mass interchangeably, but there is a difference. Mass is the amount of matter in something, and that doesn't change. Weight is the gravitational pull on a mass. So obviously there's a connection here, and on Earth, since where our gravitational pull is constant, mass and weight will both be constants. But you can imagine locations where the gravitational pull on a mass might be different. In fact, even on Earth, the gravitational pull is slightly less, for example, if you're standing on the top of Mount Everest, than if you were standing down at sea level, or the middle of, what's that place, the lowest place on Earth. Anyway, so weight is the pull of gravity on a given mass. Death Valley, that's what I was thinking of. Weight is the pull of gravity on a given mass, but that can change with location. Imagine you're on the moon. You're going to weigh a lot less on the moon, about 1/6. So if you weigh 100 pounds on Earth, that's frighteningly small. I hope you weigh more than that. You're only going to weigh about 16 pounds on the moon. But it's still the same amount of mass. You have the same amount of mass, the same amount of matter, the same amount of stuff out of which you're composed on the moon as you do on the Earth. So you can become weightless, say by going into space, but never massless. Mass never changes. So something with mass doesn't change. But weight, the pull of gravity, can change based on location. So why do people often use those terms interchangeably? Well, because on Earth, mass and weight remain constant. So people use the words as if they mean the same thing. Weight depends on mass, and on Earth it doesn't change much because, the pull of gravity is almost always the same. But mass and weight are not the same thing. Okay, the standard mass is the kilogram. And that's defined as a cylinder of platinum iridium that's kept under these special jars for safekeeping. Now, there has been a change. There's been a push to change the kilogram. Maybe it's already happened. But for decades, this was the standard weight of a kilogram. And all other kilograms were made in reference to this platinum iridium cylinder. But the unit of mass most often used by chemists, as I mentioned before, is the gram. A kilogram is often far too large an amount to work with. So if you want to identify just basic metric measures, an approximation of them, here's some nice conversions you might try to remember. If we're talking about a millimeter, that's about the thickness of a dime. If you're talking about a centimeter, that's about the width of a thumbnail or a fingernail. My pinky is about the width, is about a centimeter. So millimeter, the thickness of a dime. Centimeter, the thickness of my pinky. A kilometer, we're talking about a meter here. I don't know why this should be meter. A meter is the distance from doorknob to floor. A meter is just a little bit over 3 feet, just a little longer than a yardstick. If we're talking about millimeter, which is volume, it's about 5 drops of water. So if you had a little dropper, you squeezed out 5 drops of water, that would be a millimeter. A liter is about the size of a quart of milk. A milligram is about the mass of a speck of sawdust. A gram, which is 1,000 of those, is about the mass of a paperclip, or the mass of a dollar bill. And a kilogram, which is 1,000 grams, is about half the mass of a math book. The unit of volume most often used in chemistry is the milliliter. A cubic meter is far, far too large. So we use Now, this takes us to the topic of density. Density is one of those derived quantities. Density compares two objects that are equal in volume but have different masses. And because we're going to define density as mass divided by volume, something that has more mass per volume will have a higher density than something that has less mass for the same volume. Why do cranberries float? Here's a great picture of cranberry harvesters, and you can see the cranberries are just floating on the top of the water. Well, it's because they are less dense than water. They have less mass per unit volume. So the amount of water that they displace, but they are less dense. For a given volume of a cranberry, the size of each cranberry, that weighs less than the same volume of water. And so the water pushes it up and they become buoyant. Why does ice float? Same thing. Ice is less dense than water. That's the only way it could possibly float. It must have less mass per volume than a comparable amount of water. If it had the exact same density, then it would be submerged. It wouldn't float. It wouldn't sink. It would just simply stay wherever you put it. So the important relationship is between an object's mass and its volume. So if we look at water, a cork, which is very, very light given its volume, it floats very, very high in the water. Wood, which is heavier than cork, it floats a little bit lower, but it's still buoyant. And a metal sphere that is the same size as the cork or the wood is going to sink. So the density of cork is less than the density of wood, which is less than the density of metal. So we define density as mass divided by volume. And you'll often see this figure here. I think that's called rho in the Greek alphabet. Well, anyway, density is that ratio. Oh, and that makes sense why we would call rho for the ratio, because it's the ratio of mass to volume. So density equals mass divided by volume. The density of water at 4 degrees Celsius is defined as 1.000 grams per cubic centimeter. So keep this in mind. We're going to look at something a little longer called specific gravity, and it's going to be comparing the gravity of something to the density. It's going to be comparing the density of something to the density of water. So this is a reference. This is a frame of reference, and you'll need to know that. You'll need to know that the density of water is 1.000 grams per cubic centimeter. So it's 1 gram per cubic centimeter. That should be easy to remember, and you will need to know that. Something less dense than that, something that is only, say, 0.95 grams, is going to float in water. Something more dense than that, say 1.1 grams, it's going to sink. So ice at 0 degrees has a density of 0.917, which is slightly less than 1, which is the density of water. Therefore, something that's less dense than water will be pushed up by the water. It will float. A cubic centimeter of lead has a mass of 114 grams. So its density would be mass, 114 grams, divided by volume, 10 cubic centimeters, or 11.4 grams per cubic meter. That's 11 times more dense than water. And so it's going to sink. It's going to sink like a stone in water because it's 11 times as dense. Here is a great illustration of density. And the density of, as density changes, you'll have bands. So here you have a ping pong ball, which is the least dense here. Then you have lamp oil, which is sitting on top of rubbing alcohol, which is sitting on top of vegetable oil, which is sitting on top of water, which is sitting on top of dish soap. And what you have here is you have a soda cap, and it's floating here in the rubbing alcohol. And you have some beads, and it's floating in the vegetable oil. And you have a cherry tomato, it's floating in the dish soap, which which is just below the water. Then you have some milk, and you have something, a piece of metal, I guess, floating in the milk. You have some maple syrup, some corn syrup, and some honey. And you have a popcorn kernel that's floating here at the corn syrup level, and you have a metal bolt, which is denser than all of the above. So this shows how so we're going from the most dense liquid to the least dense liquid. And in those varying densities, certain other things are being captured, are being buoyed up. So this cherry tomato, it's just as dense as the dish soap, but it is obviously less dense than the milk. Because if it were as dense as the milk, it would have dropped down into the milk layer. But it's clearly not. It's above it, so it must be less dense. So everything that's above is less dense than what's below. What happens to the density of a substance as its temperature increases? Most substances increase in volume slightly as the temperature increases, but its mass remains the same. So what happens to its density? Remember, density equals mass divided by volume. The mass is going to remain the same, but the volume is going to get bigger. When the denominator gets bigger, the ratio is going to what? It's going to get smaller. Since the volume increases while the mass stays the same, the d must get smaller because the mass is being divided by a bigger denominator. If you divide something by a bigger denominator, you're going to get a slightly smaller answer. So most substances decrease in density as temperature increases. But water is an important exception, and we'll look at that in greater detail. But as we've already seen, water, when it gets cold, instead of decreasing in density as temperature, so in reverse is true. So most substances, they decrease in density as temperature increases, which means that as temperature decreases, they increase in density. But water doesn't. As water gets colder, it decreases in density, which allows it to float on top of water, which is why ponds don't fill up with pancakes of ice and kill everything inside. Remember, you can rewrite the density formula to solve for mass or volume, whatever you don't know. So if you know density and mass, you can solve for volume. If you know density and volume, you can solve for mass. If you know mass and volume, you can solve for density. So remember, don't just get this locked into your head one single way. Remember that you can rearrange it to solve for whatever you don't know. So you can solve for volume by just rearranging it so it's mass divided by density. So here's density. Density is mass over volume. But if you want to solve for mass, then you're going to multiply both sides by volume, giving you density times volume equals mass. So remember that you can manipulate these three different ways. Given any two, you can always find the third. Specific gravity, I mentioned, is a comparison of a substance's density to a reference density, usually the density of water, which is 1 gram per cubic centimeter. Here's the formula. Specific gravity equals the material density. So whatever material you're comparing to water, whatever its density is over the density of water. So just think of it this way: you're comparing the substance to the density of some substance to a known density, the density of water. Notice that the units will cancel. So if you divide the density of a substance by the density of a substance, remember the density equals mass over volume. Well, the mass over volume, those units are all going to cancel. And so specific gravity is one of those weird things where it has no units. In fact, if you use units for specific gravity, that's not correct. So just remember that. That's one of those weird exceptions. Because we're comparing density, we're dividing density by density, we get rid of all the units. Temperature. What temperature scale do you use to measure the temperature in your home? Well, if you're in America, you probably use Fahrenheit. And in Fahrenheit, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit, at least at sea level. But there are two other temperature scales that you need to know about, and these other two are widely used in the scientific world. Celsius, which I'm sure you've heard of, this is where water boils at 0 degrees, freezes at 0 degrees and boils at 100 degrees. So all three of these are going to use some reference points, and where water freezes and boils is a pretty common reference point. Notice there are 100 degrees separating these two reference points. So water freezing at 0 and boiling at 100, it means we've divided that range of temperatures where water freezes and water boils, we've divided it into 100 units or 100 degrees. So that's important to remember. And Kelvin is the other temperature scale. You might not have heard of Kelvin. And in Kelvin, water freezes at 273 degrees and boils at 373 degrees. Notice, however, though, this is the same thing as Celsius. There's 100 units or degrees between the freezing temperature of water and the boiling temperature of water, which means that the increments or the degrees of Kelvin are the exact same as the degrees of Celsius. Each interval is the exact same size. That's helpful. So, yeah, like Celsius, there's 100 degrees separating these two reference points. So degrees Kelvin and degrees Celsius are the exact same interval. They just have shifted starting points. So here's a way to kind of compare all three. So if we want to compare Fahrenheit and Celsius, okay, the boiling point of water is 212 for Fahrenheit, 100 degrees Celsius for Celsius. The normal body temperature, 98.6. In Celsius, it's 37 degrees. Water freezes at 32 degrees. Over here, Celsius is 0. And if we add Kelvin to the mix, this is the freezing point of water, so 32 degrees Fahrenheit, 0 degrees Celsius, 273 degrees Kelvin. We'll talk about why that number is so big, because, yeah, anyway. Boiling point of water, 212, 100, and this is just done. So just as this is 100 more than this is 100 more than this. Converting between Celsius and Kelvin is easy. You just add or subtract the number 273. As you can see, they're shifted over. When this one is 0, this is 273. When this is 100, this is 273 more. So to convert Kelvin, the bigger number, to Celsius, the smaller number, you just subtract 273. So this number minus 273 gives you 100. This number minus 273 gives you 0. So if you're starting with Kelvin, subtract 273. If you're starting with Celsius, you add 273. I'm starting at 0. To get to Kelvin, I add 273. So to the smaller, just remember, Celsius is always lower than Kelvin. So to get to Kelvin, you're going to add 273. Or remember, Kelvin is always higher than Celsius. So to go from Kelvin, the higher, down to Celsius, the lower, you're going to have to subtract 273. Okay. Gone over all that. So here, again, here are the formulas. I find it easier, you can use these formulas. I find it easier just to remember which one is higher. Kelvin is always higher, therefore you subtract 273 from Kelvin to get Celsius, the lower. And that is that's the end. Thank you for your time and attention.